Now, we saw last time we can't really make a capacitor by the simple two plates separated by air and get any decent value out of it. So what we usually do is we put what's called a dielectric between the plates. This is basically an insulator. The thing that we care about is how well we can polarize it. And what that means is we want the bound electrons to be pulled upstream and the positive charge from the nucleus to be pushed downstream. So if we imagine every atom as being like one of these little dipoles where there's a positive side and a negative side, if we put an electric field on it, all positive up here, all negative down here, it will tend to line these things up. So the negative side tries to get as close as it can to the positive plate, and the positive side of the atom tries to get as close as it can to the negative plate. The net effect of this, since all these charges are going to be canceling each other out, is negative electrons up here, positive charges down here. We have an internal field that somewhat cancels this external field. And what it lets us do is stack a lot more charge on there for a given voltage than we would otherwise be able to. That means we make a better capacitor. So the difference here between the total field and the field that we'd get without a dielectric, E naught, is this thing kappa. This is a Greek kappa. It's not a K, and it's definitely not the K from Coulomb's law. This is dimensionless because we've got an electric field divided by an electric field, and it's called the dielectric constant. And it essentially tells us how much better than a vacuum the stuff between the plates actually is. When we have a material between the plates, we have a dielectric, we change our formula from A epsilon naught over D to A kappa epsilon naught over D. So it just is just a multiplying factor. Sometimes you'll see these two pieces, the kappa and the epsilon naught, combined into epsilon without the little zero. And this is, of course, going to depend on the material, just like kappa depends on the material. If we look these up, we'll see kappa is 1 for dry air. 1 for a vacuum, 1.00059 for dry air, and you can get numbers over 250,000 for some very specialized compounds. These are the things that let you buy a 1 farad capacitor for $1 or two and be able to hold it in your hand rather than need a forklift to carry it. These materials also have their own breakdown voltages, so just because we've got a high capacitance doesn't mean we can put any voltage we want across it.